process of going from reactants to product. So I'm gonna say that you should be able to do this, and this is part of the discussion packet too. So this is just practice for the discussion packet, that you should be able to label all the coordinates, that your y-axis is the energy, that the x-axis is the reaction coordinate. So I'm gonna let you copy this if you want, that you need to know what every position meant. And every position meant that you're starting with reactants, you're gonna go through products. So we're looking at this difference in energy. And you can make up numbers if you want. So I'll wait till you kind of copy there. And so we also need to know that at the very top of the little peak, that is called the transition state. So that is the transition state, and the difference between the energy of the reactants to the energy of the transition state, there will be the energy of activation. And people need to know that, right? And I'm assuming that this is all really old stuff, right? And that I don't have to worry too much about this. Yeah? Kind of? Everybody has seen this. Yes. All right. Not that what? Not that in depth. Okay, well, we need to know this. We need to know this. When we start chapter 6, I'm gonna say, this is the energy diagram of that. That you can make numbers up, people usually can go ahead and make numbers up. If this is 0, you can just say, this is 20, and then maybe this is 30. Let's go ahead and try that just for a moment. Because last time we saw each other, we did the bond dissociation energy, remember that? And everybody understood what to do with that bond dissociation energy. Well, here, if I said, what would be delta H? I think it's a good idea that you can come up with your own special numbers. I'm gonna call this 20. May I call this 20, just because I want to? I'm gonna call this a 20 here. You could have called it a 10, I don't know what you're gonna do. I'm gonna call this the same distance, and I'm gonna call this a 30, yeah? I don't know if I'm doing this right, but I'm going to. And then I'm gonna call this a 40, just to make my arithmetic easy. Is everybody there? Obviously, this is not very well calibrated. Is everybody okay? Because this doesn't look to be, this is a difference of 20, and now this is a difference of 10. So those of you that are quite mathematician will understand. So if they ask you here, what is the delta H, overall delta H, what would it be again now? Back to what you know. Back to what you know, what would you do? Delta H of products, everybody? Delta H of products, so this is gonna be 20 minus the delta H of reactants. This is gonna be 30, so the delta H here is gonna be negative 10, which is a negative value, and that's why this is called exothermic. So you can make numbers up. This is not the bond dissociation energy. This is still delta H, okay? The energy of activation here, you can also say that this is 10, whatever the units are, kilojoules, kilocalories, whatever. I'm just making sure that you don't forget how you did things before, and that we don't mix them with the new. All right, so that from before stays the same. Everybody okay? Mm-hmm. All right, and then I don't know, this is a vertical axis, okay, potential energy, okay, whatever. All right, so what will be the difference if they say, could you do the energy diagram of a slow endothermic reaction? Okay, draw the energy diagram of a slow endothermic reaction. Okay, people are looking at me, I'm not having to worry. Okay, here we go. Draw, I'm asking you to draw an energy diagram for a slow endothermic reaction. So what do these terms mean to you? What does slow mean to you? What does slow mean to you? The slow means large energy of activation, right? So that's what that means to you. You want a large energy of activation. And endothermic means what? Energy is absorbed. Energy is absorbed. What else? The delta H is what? Delta H is a positive number. Positive number. Can I see somebody's graph that looks beautiful? She goes, don't come here. Anybody's graph? Anybody has a graph that I can borrow? Since I don't want to make a fool of myself. Hey, can I borrow hers? I'm borrowing hers. I didn't let her finish, but I'm gonna borrow hers. Okay, so I'm letting her finish. I want you to have all the points, right? So if this was it, and you wanna have all the points, there are things that are missing in here for you to get all the points. Okay, you wanna put energy on the left-hand side. Over here, you wanna call this reaction progress, or the coordinate, okay? And then over here, this is your transition state that is gonna look like that. That would be really the only thing that I would just go ahead and say that was missing, okay? Everything else would have been perfect. And everybody can see that the difference here, if we do the same thing, and this is a 10 over here, if we call this a 10 over here, and let's say this is 20, and this is 30, perhaps this is a 35 here, let's say this is 35, right? And I'm making numbers up, so you are able to make numbers up. The delta H is still the H of products minus H of reactants, okay? So your H of products is here 35 minus the 10, your delta H overall is gonna be your 25, which is a positive number, which is again evidence of endothermic. So all I'm giving you is power to give numbers to your coordinates, all right? That's all that we're trying to do here. So it's a qualitative approach. So you did a lot of quantitative approach in your other class. Organic chemists like more of a qualitative look at things. All right, let's take a look at another option. The other option that, thank you so much, and sorry for writing on your paper. The other option is that you would have a multi-step reaction. And in a multi-step reaction, what does that mean usually? That you're going from reactants to an intermediate, and from that intermediate to a product. And, okay, I don't know what this is. So let's say we have that. Try to ignore all this stuff. Try to ignore all this stuff, and I couldn't erase it, and I feel bad. But let's just take a look at the graph itself, right? So if we take a look at the graph itself, you're going from reactants to products, and if I just look at that, going from reactants to product, you're gonna say that this reaction overall is exothermic. Is everybody there? So we're ignoring all the extra fluff. If I say, when you have that little well is called an intermediate. All the chemistry that we're going to see the whole entire year either goes like the graphs before, through a transition state, or they will go through an intermediate. Is everybody there? All of it. We don't have any other type of chemistry, just through a transition state or through an intermediate. So when we start chapter 6, I'm going to say this one is just going through a transition state. And everybody sees the energy diagram in your head, okay? This one is a multi-step, which means that we're going to have to go through that intermediate. This is saying that to go to the intermediate, that this is an endothermic step. Everybody can see that that's endothermic for you to go to that intermediate, and that the intermediate to the product is an exothermic step. So you have an endothermic to intermediate, exothermic to product, overall exothermic, okay, overall exothermic. You're going to be going through 2 transition states, so you'll be having to go through transition state, the transition state, number 1, to get to the intermediate, and then the second transition state to get to the product. And I think, I don't know if you've seen this before, there is one exercise for you to do. Please get the discussion packet done prior to coming to class. I cannot even tell you the value of you doing the work ahead of time, okay? The material will start packing very soon, okay? It all starts accumulating. You cannot wait till chapter 6 to learn chapter 3. Does not work for this class. I don't know if people are studying. I mean, certainly I try to tell you to study. I don't know, I cannot force you to do it. I cannot force you to do it, but you need to be able to do. So this time they're talking about the chlorination of methane. Did you see already what step is this? What would you call this? What would you call this? There were, for the chlorination of methane, I have methane with the chlorine radical. Is this an initiation step? What is this step? How do you know it's propagation step? And it is propagation step. It is propagation step. The assumption is that you've already had done the initiation step. So you already had generated the chlorine radical, right? So the chlorine radical was already generated. The chlorine radical is now going to abstract the hydrogen, okay? And it created the methyl radical, yes? It created the HCl, and there is this chlorine that they're putting in there to destroy your nervous system, just to say that there's more chlorine in the mix. So this is a typical way to kill students in my class. Okay, somebody is taking a look at that, like, thankfully we have these papers. This was called here propagation steps. We saw that for people that are looking. The initiation step was that, where you broke the chlorine radical. This was a typical first propagation step, where the chlorine radical went after the methane, that you created the HCl and the methyl radical. So we did that already. What is confusing to a lot of our students is this extra chlorine. And what that is saying, remember that we're starting with X amount of chlorine, Avogadro's number, and not all the chlorines were cleaved at that moment, okay? So if you saw, we calculated that. This is obviously a delta H of negative 109. So this is an exothermic step. We see this as a favorable step also for the reaction. All right. Oh, I don't want to see that, but take a look. Okay, you don't need to know this. You do not need to know this. But for fluorine to work, the energy of activation is 5. Okay, this is going to turn to you like this. Okay, for you what is important is that fluorine reacts explosively. That means it doesn't work. Okay, so fluorine does not work. That chlorine reacts at a moderate rate, while bromine must be heated to react, and that iodine does not react because it is too slow. So, people are going, why do we need to know this? And I really think that the only reason that you need to know this is because at the beginning of the class, when we were looking at the reaction of alkanes, right, when we were looking at the reactions, bless you, of alkanes, this is what we wrote, okay? the reactions of alkanes, this is what we went ahead and wrote. Okay, and we wrote this. And this is all that we need to know. Remember how we said that the only halogens that work are chlorine and bromine? Remember that? So iodine is not gonna work, it's too slow, and fluorine is explosive. So that's really all that that meant to say. Okay, so let's talk about primary carbons, secondary carbons, tertiary carbons for a moment, okay? So I think we finished on, this is what I remember us finishing on Monday, before we left. Now this looks so complicated. This is not looking like a PowerPoint. I'm sorry. This is what we finished on Monday, right? So we finished calculating that, saying that if you were to go ahead and remove a primary, if you broke, okay, the bond dissociation energy is the energy that is needed to cleave a homolytic bond or to make also a bond. So it takes 410 kilojoules to break a primary carbon hydrogen bond, and it takes only 397 to break a secondary hydrogen carbon bond. So there needs to be an explanation of that, okay? We need to explain why this is. So let's take a look at something. I'll sit down and start writing, okay? So we have different types of intermediates. So we're gonna be looking at radical intermediates, right? So we're looking at radical intermediates. Okay, there are really 4 different types of radical intermediates. If this is methane, and you were to cleave a carbon and methane with a hydrogen, right, if you do that, the carbon hydrogen there, you end up having the formation of this guy, and this is called a methyl radical. We call it a methyl. I'm not even gonna write radical, oftentimes also represented like this, Me dot. Okay, remember that I said these were all radical intermediates. Okay, everybody okay? Or you can have the CH3, CH2, and if you break that carbon-hydrogen bond, because this was a primary carbon, the radical then is called a primary radical. So no longer call ethyl here, this guy is gonna be called your primary radical. So that's a primary, I'm gonna put the methyl up high so people see the difference. Is everybody able to see the difference? There's only one methyl, but you could have a primary radical be a primary produced from ethane, from propane, from butane, from pentane, from all of that. You can also have this type of a carbon where you went ahead and you broke that secondary carbon-hydrogen bond, and so this will be called your secondary radical. Or you could have broken a carbon that had a methyl, it had a methyl, it had another hydrogen, and you broke that carbon-hydrogen bond. The radical is here, and this is a tertiary radical. Okay, so this is the introduction of your radicals. So these are all your radicals, right? And so primary radical, methyl radical, secondary. Let's take a look at the table, and I hope people can see this well. I don't know if the blue is gonna show up there well. But when I take a look at this, and I start with methane, for me to break a hydrogen from a methane to produce the methyl radical and hydrogen, it takes 435 kilojoules. That means you have to apply 435 kilojoules to break that carbon-hydrogen bond homolytically, and you generated the methyl radical. I'm gonna do the same thing with propane, and remember that propane had two different types of carbon. Propane has primary carbons. The hydrogens on primary carbons are called primary hydrogens. Propane has a secondary carbon. The secondary carbon has hydrogens that are also called secondary hydrogens, okay? And when I break a primary carbon-hydrogen bond, it takes a lot less energy. It only took 410. So the mentality is it takes less because this then is more stable than that. Your intermediate is more stable. That's why it took less energy. At least this is how organic chemistry see it. And it makes sense, okay? When I take a look at the propane, and now I'm breaking the secondary hydrogen from the secondary carbon, it even took less yet. Okay, so it takes even less energy to do that. What is the mentality once again? Well, this radical then is more stable than that because it takes less energy to break that secondary carbon-hydrogen bond. And the last of the story is when you have that tertiary carbon with the tertiary hydrogen, and when you break that bond, it takes even less energy to do so, right? It takes even less energy to do so. So, there is a trend, this is the bond dissociation energy, there is a trend that your book writes that personally I don't like, but here it comes. And I don't memorize things like that, so I'll show you, and then I'm gonna do it my way. And they're saying the stability of the free radicals. I like to go always from large to small. I don't know how you guys like to go. Do you have a preference? I always like to go from large to, I'm always trying to lose weight. Not always. I don't even know why I still insist, because my trend is going the total opposite, no matter what I do. All right, so I'm gonna put my trend the way that I like to memorize, okay? And then you can look at your slide, and you can do that in the order, but I'm gonna do them all in that order, okay? So my stability of free radicals are gonna go like this. So the stability of free radicals, and we're gonna introduce many species today. So I wanna make sure that everybody knows that the tertiary radical is more stable than the secondary, it's more stable than the primary, it's more stable than the methyl, okay? So that's the way that I like to do the stability of the radicals. I would like to go ahead and show you yet another way that we will memorize this, okay? And the other way that you want to kind of memorize this is that your tertiary radical really looks like that. Again, your book doesn't show it like this. I must show it like this. A tertiary radical is sp2 hybridized. So I'm going to represent it like this. And like this, these guys are all R groups. They don't all need to be methyls, by the way. Is everybody there? Again, I don't like the way your book does this. So we're doing it my way, because eventually I will write the book. All right, is secondary, the only difference of a secondary is right here. You're gonna keep one R, you're gonna keep another R, and now you're gonna have a hydrogen. And that will be your secondary. Is everybody able to see that? So just because the beginning was methyls, it doesn't mean that these guys all have to be methyls. It could be someplace else, it could be somebody else. When I go to the primary, again, the difference is I have one R, now we have hydrogen and hydrogen. And the last one, when the methyl are all hydrogens instead, okay? This is the less stable, least stable. Okay, and it goes like that. Yes?
Why is it least stable when it has the most hydrogens attached to it? Like carbon bonds, four bonds?
There is some little story that I will tell later Supposedly this is more stable because there is a donation of electron density between a carbon-carbon sigma bond that doesn't exist here. In reality, it's the table. So they measure the energy, it takes a lot more energy to break that one, and then we come up with a story. But it all happened to be with energy, okay? All right, so let's take a look at propane for a moment, okay? We did propane for a moment last time you were here. We did the calculations here, right? We did the calculations here. So we did this on Monday before we had to run out of here. We did that and we did that, right? And then somebody went ahead and analyzed the mixture. Okay, somebody went and analyzed the mixture. This we can do, right? This we can do by if we give you the table. I already have written the exam. There might be some calculations on the test, so you did this in the test. And this is if somebody said, draw the products of the bromination of propane, la-di-di-da. If somebody said to you, draw the major product. So let's add that story to the mix now. So what if somebody says, draw the major product in the mono bromination of propane. So now the question is a little bit different than the Monday's class, right? Monday's class we say draw products for the bromination of propane, right? So when somebody asks you this question, I'm gonna come out here and I'm gonna start with propane, and I'm gonna put bromine, and I'm gonna go ahead and put the light, and I'm gonna realize that propane had two sets of equivalent hydrogens. The sets here at the end, like chicken feet in orange, would prepare or make a primary, right? These guys will be a primary, while over here, this will be the secondary hydrogens. For those of us that need evidence, somebody did the calculations of that. You know, some people really need to, but why? Here you go. Somebody took the time to do this. They went ahead and they did bromine. They did bromine with a propane. They added light, and bromine needs heat. So not only was it light, but heat. But when they analyzed the mixture, only 3% of the product was with the 1-bromopropane. Only 3%, while 97% generated the 2-bromopropane, okay? Even though the ratio, is much greater. So everybody, there are six primaries, and there's only 2 secondaries. Nonetheless, the secondaries are 97 times as reactive as the primary. What does this translate to you? Okay, you know, how would this translate for you? Okay, because I'm not going to memorize this either. For me, what this chart is telling me is if you have a reactant like propane, and you have the option of having sets of equivalent hydrogens, and you have the possibility of different intermediates, the bromine is more selective for the most stable intermediate. Meaning, a secondary radical is more stable, your major product is going to be the secondary production of the bromine, okay? I'll answer your question in a minute. So when we finish this, and I say draw the major, my expectation is that you know equivalent hydrogens, that you know primary versus secondary, right? So everybody's seeing all that I'm expecting people to know in order to answer this. That you know sets of equivalent hydrogens, number one, that you know the type of carbons that they are, that you know the stability of the radicals, and the selectivity of bromine. So when you finish this problem, and you come here, and you put your bromo on here, and you put your HBr, this student is gonna get all the points. If you put the bromine on carbon number one, you're not gonna get all the points because that is not correct, okay? Everybody okay? You were gonna say.
Yeah, so, the thinking should be that with the inequalities, the tertiary is more stable, so it's more likely to occur, whereas, and then down the chain, so whatever's more stable is more likely to occur.
Right. So if you have the option, for example, right, so let's do another problem. If I come over here and I go ahead and draw that, and you're putting bromine again and light, and we don't care about anything else, and I say draw the major product, well, what's gonna happen here?
They're all the same.
They're all the same, right? So they're all gonna be the same, and really, what a silly question. I doubt very much that this will be a question on your test, because that would be like, whatever. But that was one of the questions on the Wade test bank. It's like, really? No. Really? No. You know, it's like, come on. So you can really turn this question into something more beneficial, and that is the last question on the packet. There's the last question on the packet that really kind of mentions that. So in that last question of the packet, if we go ahead and we look at this one, and we do the exact same thing, what will be the major product here?
The tertiary.
So I think the first thing that people need to do, okay, this is the first thing that we need to do. We need to look at the types of carbons that you have on this starting material, right? And this is gonna be called propylcyclopentane, and we're looking at the types of carbons. How many different types of carbons do you have in this compound?
Primary, secondary, tertiary.
There are three. There are primaries, there are secondaries, and there's tertiary carbons. How many primary carbons do you have? One. Hopefully you don't put the bromine there, because you're gonna get no points, is everybody. Primary radicals are very unstable. That will be the intermediate. How many secondary carbons do you have? Too many, in my opinion. Too many. There's 1 and 2. There's 3, 4, 5, and 6. There are 6. Are all the secondary hydrogens equivalent?
No.
I hope everybody sees immediately no, right? Are all the secondary hydrogens equivalent? The answer is no, okay? These hydrogens here, gosh, are not equivalent to those there, right? I mean, I hope people see that, obviously, no? What about these two here? Are these hydrogens equivalent to that?
Yes.
Okay, remember the what if. The what if. If I took one of these and I put a bromo there, okay, put the bromo back out, take the hydrogen in, would that be the same as if I put a bromo there?
No.
Okay, that is the what if. A bromo here is different than a bromo there. So these guys are not equivalent to each other. Is everybody following that? What about these hydrogens versus these hydrogens? Are they equivalent? Yes, these guys are. Okay? Is everybody with me? If you're not, please speak up. There might be another voice that doesn't sound like mine that will get the point across.
Can you repeat that one more time?
Okay, let's repeat that one more time. These hydrogens here, if I take any one of those, there are 4 there, okay? If I take one from here and I put the bromo there, okay, that will be like 1 bromo, 2, whatever this is, right? So if I put a bromo here, let's put it there for a minute, that looks like 1 bromo, 2 propyl something, okay? Take it off, take it off, take it off, and put it here, isn't that the same thing? If I put it there, you see that they're the same thing?
Yeah,
So if they're the same thing, then you go back and say those hydrogens are equivalent. Okay, that's what I keep playing the what if scenario, all right? Now, instead, if we're looking at now these hydrogens over here, at that end, you know, those hydrogens at the end, again, the same thing. If you put the bromo here, this will be 1 bromo 3, or if you put the bromo here, that will be 1 bromo 3. So again, these guys are equivalent. Very different than if you put the bromo here. The bromo here now is in the side chain. And this will be that will be parentheses, 1 bromopropyl cyclopentane, right? Or if you put the bromo here, that will be parentheses, 2 bromopropyl cyclopentane, right? So they're all 4 sets of equivalent secondary hydrogens, But the most important thing is that there is a tertiary carbon. The tertiary carbon is here, and that tertiary carbon has only 1 hydrogen. If they're asking you for the major product, bromine is super selective for that tertiary position, because that tertiary position produces the most stable intermediate. So the major product here is just this guy, okay? And anything else will not give you any points, because that's not the major product. Very differently than if somebody says, how many possible, look at the other option, this is major. How many possible, we don't care about the rate, how many possible mono-brominated compounds. For the example above, right, we're talking about the example above, yes?
What if you had 2 tertiary carbons?
Okay, one moment, let's just finish one thing.
Okay.
Then it would be a disaster of a question, because you would have to go after both. So, you know, you would go after this tertiary and after another, and then we look at other things. Okay, so can we finish that? How many possible monobrominated compounds would you get from this reaction? Now it's not major, we're not asking major, we're asking possible.
5. 6.
A is 3, B is 4, C is 5, D is 6, E is 7. I have no idea. They're telling me 6.
6.
Are people agreeing on 6? I'm not sure. Is everybody agreeing on 6? Well, we just went around the crazy ring, so that would be 1, 2, 3, 4, 5, 6. The correct answer is 6. There are 6 possible. What is the ratio? I have no idea. Even if it's 0.01, that's possible. Okay? So even if it's 0.01, that is possible. So that's what we're looking at. All right. Let's take a look at other intermediates. Let's take a look at other intermediates, okay? These are other reactive intermediates. This is kind of like the end of chapter 4. Are we all okay? Nicole? Yeah?
Yeah, I mean, I was just thinking is it 100% of the time always gonna be on the most stable carbon?
Well, the question is not 100%. The question is possible. And when we're asking about possible, the term possible is really saying how many positions are unique and different from one another. That's really what possible means. Okay, so possible, we went through that story that you have a primary carbon. Would it be possible, or would it be a high percentage that you put the bromine there, I'm telling you that this is gonna be a trace, but it's possible, all right? So we need to all make sure that we play the game the same way. It's possible, anything is possible. Look at the fires in Middletown. So when they're asking about possible, when they're asking about possible, all they really are wanting to know that you recognize that there are different types of carbon, that there are different types of hydrogen, and which ones are equivalent. That's really what the question is asking here, equivalent. If I put equivalent, people should then know it right away, okay? Is everybody okay? Not I. I'm glad you're okay. I'm choking you to death. Here are some reactive intermediates. So we introduced the radical already. I will copy this while I suck on this for a while. My reactive intermediates. Radical is just having the odd electron. Reactive intermediates, these are all intermediates. We're gonna see them all through the whole entire year. So every time we get to another chapter, we'll be introducing them differently. I think we have already talked about a carbocation. We've already talked about the radical. We've talked about the carbanion. And now we're introducing the carbene. So I think the only one that we have not seen yet, is the carbene. These things, these intermediates, the word says it all, they are intermediates. We don't buy these things like that. If you were to buy a carbocation, it would have to be with a counter ion, like a methyl chloride or somebody like that. They are really short-lived. They are intermediates, they are short-lived, but they will be seen in the whole entire semester as how to get from one to the other. For the alkanes, this is the reactive intermediate. So in the chemistry of the alkanes, what we're seeing is just this guy. This is the reactive intermediate in the alkanes. We'll introduce all the other ones as the semester goes by, but we need to know them all like today. So let's take a look at them separately. We've already talked about a carbocation. Take a look at how a carbocation is. What does that mean? What is this telling you? The carbocation is then sp2 hybridized. Your carbocation is sp2 hybridized. The carbocation has an empty p orbital. So anybody that comes with a pair of electrons, they will go ahead and attach that. That doesn't. I don't know what has happened. Something occurred. All right. I don't know about that. Okay. So that's the stability of the carbocation. The stability of the carbocation is just like the stability of the radicals. So you need to know this. Stability of carbocations is exactly the same as the stability of the radicals. So I'm trying to remember. You, Michelle. Oh? No, Amber. All right. So Amber said, why at the beginning when I was saying that the methyl radical is less stable than a tertiary radical. A lot of what organic chemists do is there is somebody out there that is doing all the calculations in the world, like the table that we saw before for a bond dissociation energy, right? So that's the first thing they do. We take a look at that table, we don't memorize the table, we seldom do numbers, we look at the trend, okay? So we look at the trend, and the trend says that the tertiary is more stable than the secondary, than the primary and the methyl, and then we come up with a story. Seriously, that's my best way of explaining this. And when I come up with a story, here comes the story. The story begins that they are stable in two ways. The first way is what is called an inductive effect. And the inductive effect is said that there is a donation of electron density along the sigma bond. Well, you know, to me, I'm sorry, Wade, but you're missing something. Right? So this is saying that inductive effect, and you have to memorize it. This inductive effect is the donation of electron density along the sigma bond. And so I need to add a little bit more than that, right? Can I go back a slide? I mean, are these all sigma bonds? Right? Something is missing in that definition here to me, because these are all sigma bonds. So the inductive effect is really a donation of electron density through a sigma bond of a carbon-carbon bond. I would add that to my definition because that's just not enough. Donation of electron density along the sigma bonds of carbon-carbon, because we had carbon hydrogens there. So it's carbon-carbon. Anytime, the more carbon-carbon bonds that you have, the higher the electron density. I don't know if they did a drawing. I don't know if they did a drawing, but this is the way that I like to see it. May I write on my notes? Because I don't know if I like the way they did stuff. But again, I don't have patience to do PowerPoints. And because I'll never forget, I can do it here. So this is how I see the stability of a carbocations. So stability of carbocations. And again, I know that they are sp2 hybridized. So since I know that they are sp2 hybridized, I'm going to draw them like this. And this is kind of like an sp2 way. And this is my tertiary. And this is how I see the inductive effect. I put a little arrow. I put a little arrow. And then at the end of the day, the more arrows I have, the more I believe that I'm the more stable. When I come over here, and again, I do my little arrows, that's the inductive effect. This is really easy for me to remember. So that definition, in my opinion, is missing stuff. Because when I get to the methyl that is the most unstable, there are none of these. So there are no of them here, okay? So that was number one. This is the little arrows is my inductive effect. And so the same thing is true. The same story would apply to the radical. The radical is electron deficient, right? The radical is electron deficient. The radical really, really wants electrons to itself too. So the second story of why a tertiary carbocation or a tertiary radical is more stable is called a hyperconjugation. Hyperconjugation is a little bit more difficult to explain. They're saying that this is and it's really a secondary, by the way, but it's an overlap of a sigma bonding orbitals with empty p orbitals. This is what they're referring. Is everybody? If we're looking, obviously, yeah, wait till you're done copying. Hyperconjugation is an overlap of sigma bonding orbitals with MTP orbitals. So if you take a look at that carbocation, what type of carbocation is that? This one. Hello, I'm growing older. What type? Is everybody agreeing this is primary? Yes or no? Well, that carbon is bonded only to one carbon, and you have two hydrogens, so that's a primary carbocation. Okay, a primary carbocation, of course, is bonded to a carbon, and the simplest of that carbon is that carbon is sp3, right? And there's that sigma bond between that carbon sp3 to the hydrogen, and they're talking about this weak overlap. This is what is called a hyperconjugation. I'm one carbon away, and there's this weak overlap between these electrons that are here. I don't have any. Okay, this is another I believe story. I mean, I'm telling you, this is like my religion slide. This is my I believe slide. The song, I believe in children, this one's mine. The more of these that you have around, then the more you would have, right? So if you have another one the same and another one the same, then more the hyperconjugation that you would have for that one. Same story for the carbocations, same story for the radicals, so they both have that same story. When I get to, all right. No. All right, so it's the same thing. They have the same thing for these guys, right? The same thing for the radicals. They look exactly the same way. We already put that there, right? Now take a look at, again, the same thing over and over and over again. Now we're going down like I had it. We did this already. Let's take a look at the carbon ions. If we take a look at the carbon ions, immediately what is this showing? Carbon ions are sp3 hybridized. Do you see it, the way they have it? They're even telling you that they're sp3 hybridized. So your carbon ions are sp3 hybridized, okay? And you have a total of, a lone pair there. So carbon has a negative charge, the stability, okay, I'm sorry. This is what happens when you have PowerPoint. Click, 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 click. Carbon ions, would it be the same stability order as the carbocations? Okay, so this is a critical thinking moment. The carbocation was, a tertiary carbocation was very stable, right? Tertiary carbocation, here we go. Tertiary carbocation was very stable because you were able to donate electron density through inductive effect and hyperconjugation. What about the carbanion? Does it need that?
No.
Doesn't need it. I already have too many electrons. It's everybody. So the carbanion is the total opposite of this. I don't want any of this to happen, right? So in the case of the carbanion, you should have the total opposite of it. Your carbanion, the most stable, right? In the stability of the carbanions, you want it to be the total opposite. These guys are sp3, well, most of the time, but you don't want all of them. You already have them. I'm gonna draw them like this, kind of to show sp3. So your methyl is definitely gonna be more stable than your primary. Your primary is going to be more stable than your secondary. And this guy's going to be a lot more stable than the tertiaries. And everybody can see why, right? People can see why. if you're donating, you don't want electrons. This guy is negative, right? This guy is totally negative. If you're donating electron, like we said, the inductive effect is donating electron, there's gonna be repulsion. So it's the total opposite of the stability of the
So it's
carbocation.
just saying.
Right, right. You want hydrogens, you don't want more electrons, so you want H pluses. You don't want any more of this. And I think the way, if we go back to that slide, we go back to the slide and they're telling you again, this is the way that this is showing, the carbon has a negative charge. That carbon with a negative charge is going to be called nucleophilic. Remember how we talked about nucleophilic? You have your electron rich and of course your basic, you want an H plus amber like you said. Okay, and this stability, whoa, sorry, they're nucleophilic and basic. And then when you go to the next one, the stability of the, I don't like the way they do things. Forget it, you saw how we did it. But they're telling you that the alkyl groups and other electron donated destabilize the carbon. You don't want them, you don't want them. You want as many space, you're already rich in electrons. They're the total opposite of the carbocations and free radicals. The last of these, no, let's let this go, are the carbenes. So let's take a look at the last of the stability of this, and we're looking at the carbenes. The carbenes, the only way to explain carbenes is your carbon before, do they show it here or they don't? No, they don't. Okay, so for me, the carbenes, the only way for me to explain carbenes is this. I don't know if you remember when you have, I'll come back to this. So in the case of the carbenes, when you're looking at carbenes, and carbenes are carbon, dot, dot, and like that, whatever these guys are. Okay, when I look at the carbon before, remember that carbon has 4 valence electrons, right? So atomic carbon, in the 2s, it has 1 and 2, and in the 2p, atomic carbon, this is carbon, atomic, before we go ahead and hybridize it, and in the 2p, it has that. Okay, see the story? I have an empty p orbital, I have the empty p orbital, I have the lone pairs, and then I have my 2 unpaired electrons. So that's how the carbenes are. So for me, the easiest way to explain a carbene, because these guys are also sp2 hybridized. So all of your intermediates are sp2, with the exception of the carbanion, with one moment. Okay, is everybody there? All of them are sp2 with the exception of the carbanion, except one moment if you have resonance structure. So we'll finish with that in a minute. So take a look at the story. If I don't hybridize this, if we don't hybridize that, but they're telling you that we must, that is sp2 hybridized, and the reason why they're calling it sp2 hybridized is because you have that empty p orbital. Is everybody, is the empty p orbital. Is everybody okay? I cannot buy carbenes. We will make them on paper, and then you will add it to the reaction. We don't buy them. We make them and react them. And I think the last thing that they want you to know is that the carbene is neutral. Carbene is neutral. Well, so are the radicals, right? Radicals are neutral. Yeah? Yes or no? Are radicals neutral? Are they neutral or not? Let me go back and check that. Are they neutral? Well, they're reactive, but do they carry a formal charge? That's what neutral means. Reactive and neutral are 2 different things. Are they neutral? They are neutral. 4 minus 4 is 0. That's what they meant. These guys are not. This is 4 minus 3. That's a plus. These guys are 4 minus 5, that's a minus. The carbenes are neutral, that's kind of important, but so are the radicals. Carbene and radicals are both neutral. All right, let's talk about that story about the sp3. These guys are neutral. Okay. One last time, and I think this is like the best thing, to just tie chapter 1 resonance with chapter 4. Okay. What is the hybridization? Of the following. So I just put of the following. Okay, and I'm gonna come over here. Alright. Something that causes a lot of problems to our students, so we wanna make sure that we finish this off like that. And we wanna know the hybridization of the ions. And we just finished saying that the carbon with negative charge are sp3. Okay, we said that. All over the book will tell you that. Carbons, dot minus are sp3. Unless you can move the electrons around, okay? So when I look at this one, is this species, what is the hybridization of that carbon? You said it was sp3, I'm gonna write there sp3. What is the hybridization of that carbon?
It can change. sp3, but you can,
So sp3,
but you can move the electron.
but not quite, okay, but not quite, because you need to look at the resonance form. Okay, you look at the resonance form. If you can do this, if you can move this pair of electrons here, and that to the top, and now this new structure looks like this. This is a CH3, this is a C now, O, dot, 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 dot minus, and here you have that. Now what happens to that carbon?
sp2.
It's sp2. Is everybody there? Can everybody see that that carbon is sp2? So the answer is, you back over here, that is sp2. If you have the option of coming up with a resonance form, right, if you have the option to come up with a resonance form, and in that resonance form, you can move it, then that carbon is said to be sp2, hybridized. Over here, were you able to move it?
You find the most favorable resonance structure and then you decide what the hybridization is.
Right, so like over here, when you're looking at this one, and you try to do a resonance form, you cannot. Everybody? You cannot do another resonance form there. So the answer is, before you start writing, is it sp2 or is it sp3? You don't memorize things here. I mean, the bum rap about organic chemistry is that people go, oh, there's so much to memorize. Well, not true. There is a lot to memorize, but there's a lot to understand and apply. Because you memorize that these guys are sp3, and if you mark that one as sp3, I'm gonna mark it wrong. I'm gonna mark it wrong. So you're looking at the option of moving the electrons. If you're able to move the electrons, if you can come up with a resonance form, the only way that this can happen is if that lone pair then was in the MTP for you to be able to do a pi bond. You cannot do a pi bond without having electrons in a non-hybrid group. Yes?
If you asked a question like that, would you be expected to show the resonance form in order to show that it's sp2?
I don't think so. I mean, if this is a, let's say this is like a multiple choice, probably I would just have SP, SP2, SP3, then you don't have to. But the only way to get the right answer is for you to be able to see if you can move them around. If you cannot move them, then they're SP3. Is everybody clear? If you cannot move them, they're SP3, don't get them wrong. They're called so a methyl carbon ion will always be SP3, right? A methyl carbon ion will always be SP3. There's no resonance form for a methyl carbon ion. Okay. All right, I'm done with chapter 4. Woo-hoo-hoo, yes?
What's the stability of the carbenes?
There's nothing. Carbene is just one thing. There's no primary, secondary, tertiary. Carbene is just carbene. There's not more than one option for carbene. All right, so the carbene is only one. There's no primary, secondary, tertiaries. Okay, so I really am done with this chapter, done. I don't think, the chapters seem big, large, right? It seemed like really big, but a lot of the chapter we really are not doing. Oh, I think I forgot the Hammond postulate. All right, so we'll start Monday with the Hammond postulate, and then we really are done.